Welcome back to McMaster University course, Computer Science and Software Engineering 2FA3, Discrete Mathematics and Applications 2. I'm Bill Farmer, and we are going to continue with the second topic of the course, Recursion and Induction, and specifically, we're going to talk about structural recursion and induction today. We're going to begin with the notion of inductive set. An inductive set, or also known as an inductive type, is a set S of values that are defined by a finite set of constructors. The constructors take certain arguments, as we see here, these S's, and they return a member, or you can say they construct a member of S. And this is done in such a way that each member of S is constructed in exactly one way. So there's a slogan that goes with this called no junk and no confusion. So an inductive set has no junk and no confusion. No junk means that there is no member of S that is not obtained by constructing it. And no confusion means that if we take any two constructions of members of S, those constructions will construct different members of S. In other words, there's only one way we can construct each member of S. Now, S is recursive if some of these arguments, sets, are S itself. In that case, we are building, using that constructor, we're building members of S from members of S. Now, a recursive definition is well defined if and only if it contains a member, at least one member, called a base case, that is not constructed from other members of S. So these argument sets, none of them are S. We need at least one constructor of that form, which is the base case. Now these constructors, if we put them together, we can define a language of expressions using these constructors. And this language of expressions, they serve as literals for members of S. They literally tell us how the member of S is constructed. Now, a definition of S induces a structural induction principle. So this principle has the following form. It basically says a property holds for all members of S, provided for every constructor. If the property holds for the components of the constructor which are in S, it holds for the constructor applied to those components. Or less formally, the property holds for all members of S, provided it holds for all members of S having minimal structure, and it holds for the structural combination of members of S whenever it holds for the members themselves. Now, a function f can be defined by structural recursion using pattern matching. So the way this works is each recursive application of S must be applied to at least one argument of reduced structure. So if f was applied, if f took 3 arguments, it would have to be applied, at least one of those arguments would have to have reduced structure. And we define f using several equations, one for each pattern, and we have at least one pattern for each constructor. Okay, so here's a question. How many constructors are needed to define the natural numbers as an inductive set? You can stop the video and think about this for a moment. Okay, welcome back. The answer is 2. B. We'll see this in just a moment. So this example shows how the natural numbers can be defined as an inductive set. So let's say we have a set nat it's meant to represent the set of natural numbers. And we have two constructors, 0 and s. Now 0 doesn't take any arguments. Basically 0 is a constant. It's a name for a member of NAT. And s takes a member of NAT and returns a member of NAT. So because of this argument being NAT, NAT is recursive. And the members of NAT correspond to these expressions: 0, successor applied to 0, successor applied to successor of 0, and so forth. And these expressions, they're literals that denote these members of the natural numbers. And then we have an induction principle for NAT, which is given as follows. And in this induction principle, we have two conditions, one for each constructor, one for 0, one for a successor. And because 0 doesn't take any arguments, the condition is that the property holds for 0. And because successor takes one argument, which is a NAT, our condition is that the property for all x, if the property holds for x, it must hold for the successor of x. So if these two conditions are true, then we know the property holds for all x. This is the structural induction principle for NAT. And the amazing thing is, this principle is weak induction. So weak induction is the structural induction principle for the natural numbers when we have these two constructors. Okay, so now what we're going to do is we're going to define some function recursively using pattern matching. And so the first function is we're going to find plus, and the patterns are going to be here 0 and the successor of 0. And so basically we're going to have x plus 0 will be x, and x plus the successor of y equals the successor of x plus y. And if you think of this case, it's basically saying x plus y plus 1, like this, equals x plus y plus 1. And you can see those are obviously equal. Now the important thing here is that the structure of this is the successor of y, and the structure of this is just y. So you can see the structure has been reduced. That's why this definition makes sense. So multiplication is similar. We have, let me change the color here. We have the same two patterns, and we have x times 0 equals 0, and x times the successor of y equals x times y plus x. And what we have here is x times y plus 1 equals x times y plus x. And you can see that we can get from here to here by multiplying x times y. Okay, so this makes sense. The final function is the fib function. This is a function that takes a natural number n and gives the nth Fibonacci number. And it's defined by pattern matching, but here we have three patterns: 0, successor of 0, and the successor of x. Notice these three patterns cover all possibilities. So fib of 0 is 0, fib of the successor of 0, which is fib of 1, is successor of 0, which is 1, and the fib of two successors of x equals a fib of the successor of x and x. And notice both of these have reduced structure. Their structure is smaller than what we have here. Okay, so here's an example of using structural induction for the natural numbers. So we would like to prove that for all x, x plus 0 equals x. Now you may say, well, isn't that what we just defined? Well, no, it's not just what we defined. if we go back up here and look at this, we define addition as x plus 0 equals x, not 0 plus x equals x. And you may say, well, isn't addition associative? Or I should say, in this case, commutative. Isn't it commutative? Commutative means that x plus y equals y plus x. Well, it is commutative, but we don't know that yet. We have to prove that. That's something that needs to be proved. So as a starting point, we're going to prove that 0 plus x equals x. So here's the property. The property of x is that 0 plus x equals x. And we want to prove this property to be true for all x in that. And we're going to do it by structural induction. So our base case will be that x equals 0. And we must show that p of 0 holds. So p of 0 equals, the property of this is that 0 plus 0 equals 0. And we know that this holds by the definition of p, because that's an instance of this. That's part of the definition of addition. It's right up here. So we know that. And that means that p of 0 holds. So now the induction step is we're going to look at x equals s of y. And we're going to assume p of y. We're going to assume that the property holds for the argument of our constructor. And we have to show the property holds for s of y. Now, 0 plus the successor of 0 equals s applied to x plus y. The successor of, I should say, 0 plus y. That's because this is an instance of one of the equations that define plus. It's right up here. Right here it is. Okay, now we know that p of y holds, and we know that this is the property. So we know that 0 plus y equals y. So we know that, well, we know that this is the induction hypothesis. That's an instance of the induction hypothesis. And then we know that 0 plus y is y, so because of this we can replace it with y, and we get this, and that's the instance of, this basically is p of s of y. And we are done. We've shown p of s of y, therefore the theorem holds by structural induction. Okay, so we have another question here. Let's say we have a constructor, C, it's right here, defined like this, for an inductive set. And the statement says that this produces a base case if which of the following is true. So you can turn off your video, think a moment, and answer this. Okay, welcome back. There's actually two answers. The first answer is that there are none of these SIs. In other words, C is zero area. It's like the zero constructor for now. So this is correct. The other is that none of the SIs are S. There's something else, not S. So this is okay. C and D are wrong. C and D are not base cases. Only A and B can be base cases. Okay, so let's look at another example. This example is binary trees of natural numbers. So we're going to define a set called bin tree. It's an inductive set that represents binary trees. So what is a binary tree? It's a tree that looks like this, or like this. And the tree has natural numbers at every node. So we could have 2, 3, 4, 1, 1, 2, 1, 2, 3, 1, 5, something like that. So if we look at one of these trees, we have two kinds of trees. We have a tree which is just a leaf and a natural number. So it takes a natural number and returns a bin tree. Or it can be a branch. It can be constructed by a branch constructor, which takes a bin tree and a natural number. And if we look at it this way, if we look here, here's the natural number it takes. Here is the left tree. Here is the right tree. So it takes these three arguments. So bin tree is a recursive inductive set. Here's the induction principle. We have to have two conditions. One condition for each constructor. We have two constructors. The first condition says for all natural numbers, the property holds for leaf of n. The second one says for all natural numbers and all trees T1 and T2, if the property holds for T1 and T2, because T1 and T2 are members of this set bin tree, then the property holds for the branch constructor applied to T1, N, and T2. And if these two conditions are true, then we get this result which says the property holds for all members of bin tree. So that's the structural induction principle for bin tree. So here are some functions we could define by pattern matching. So the first one is nodes. Nodes is a number of nodes in a tree. And we have two patterns, leaf of n and branch T1 and T2. So the number of nodes in leaf of n is 1. Remember, that would be a tree like this. And the number of nodes in branch T1 and T2, which will be a tree like this, where here we have the tree T1 and here we have the tree T2. It's going to be 1, which is this node, and the number of nodes in T1 and the number of nodes in T2, and these are recursive calls. And notice T1 and T2 are components of this constructor. So that's the function nodes. The function sum sums up all the natural numbers of these trees. And it's defined again by the same patterns. Sum of leaf of n is just going to be n. That's the natural number that would be attached to a leaf node. And sum of branch of T1 will be n. The number is assigned to that, attached to that node, plus the sum of T1 and T2. And then the function height, it takes a binary tree and gives us the height of it. And we're going to find the height of a leaf node is 0. And the height of a tree built with a branch constructor is going to be 1 plus the maximum of the height of T1 and T2. Okay, so here's a question. Let T be a member of bin tree. Which of the following formulas is true? So these formulas relate the number of nodes in a tree to the height of the tree. I'll give you a moment to think about it. Okay, welcome back. Well, let's look at some examples. Let's take this example. How many nodes are, let's call this T, 0. So how many nodes does T0 have? It has 1. And its height, because it's just a leaf node, is 0. So that would say that number of nodes is 1 equals 2 to the 0, which is 1. So this looks like this works, but let's take a little more complicated tree, like this. The number of nodes here is 3, And the height is 1. So this would be 3 equals 2 to the 1. This does not work. And this does not work. This works because we have 3 equals 2 to the 1 plus 1 is 4 minus 1. But notice we have two choices here. Is it always this, or is sometimes it's less than this? So let's take this example. The height of this is 2. The number of nodes, you can see, is 5. 5 does not equal 2 to the 2 plus 1, which is 2 to the 3, which is 8, minus 1 is 7. 5 does not equal 7, but 5 is less than or equal to 7. Okay, so the correct answer here is D. Okay, so let's look at an example of structural induction for bin tree. So we're going to prove what we just talked about before. We're going to prove that for all t, the number of nodes in t is less than or equal to the height of t plus 1, and then we subtract from that 1. Okay, so this is our property. Whenever you do a proof by induction, you always need to write down the property, and we're going to prove that this property holds for all members of bin tree by structural induction. And the base case is t equals leaf of n. And when t equals leaf of n, we know that the number of nodes is 1, the height is 0, and then we know that this holds because that would be 1 equals 2 to the 1, which are 2 to the 1, which is 2, minus 1, which is 1. Okay, so we know this works. Let's look at the induction step. So we have this kind of tree. It's built from a branch constructor, and we're going to assume that the property holds for both of these, and we're going to show it holds for the whole tree. Okay, so by the definition of nodes, we know the number of nodes of t equals this, and then we know that these two things, we have these equalities by the induction hypothesis because the property holds for t and t1. And now it's just arithmetic. We have these two amounts here, and if we know that this will be less than or equal to, if we take these two amounts and replace the height of t1 and height of t2 by the maximum height of t1 and t2, which possibly makes it bigger, and we have two of them, so we have 2 times that, and then we have 1 here and 2 minus 1 and minus 1, which would be minus 1. And this is the same as 2 to the 1 plus this, minus 1. And this is the definition here of the height of t. And that's what we needed to show. And we know the proof or theorem holds by structural induction. Okay, so we're going to stop here. Next time, we're going to start with orders.